Hello and welcome everybody to the course Autonomous Navigation for Flying Robots. In the previous videos we have introduced 2D geometry and then illustrated how that can be used to compute odometry for a two-dimensional planar robot. Of course, quadrupeds live in a three-dimensional world, so in this video we will now extend that to full 3D. Similar as before, we can now define points in 3D. And a 3D point, of course, consists of 3 dimensions for the x, y, and the z-axis. And again, we can augment such a vector by a 1, an additional row at the end, which is then called an augmented vector again. And we can define homogeneous coordinates or a homogeneous vector that has 4 elements. And remember, 2 homogeneous vectors are representing the same point in 3D if and only if they only differ by scale. And then using such points, we can now define a line in 3D. There are different ways of representing lines. A very simple form is to just use 2 points, and the line connecting these 2 points is then defined, can then be defined as a linear blending between the coordinates of these 2 points. So in this formula, if lambda is 0, then we're exactly at point P, and if lambda is 1, then we are exactly at point Q. And for any values between 0 and 1, we would interpolate between P and Q along the line segment joining these 2 points. And if lambda can take any real value, then we're moving along the infinite line defined by these 2 points. We can also define a 3D plane. A 3D plane can be described with 3 parameters in principle, but it's easier to use the homogeneous representation. This vector m here, m tilde, has 4 coefficients, and if you multiply that with a 3D point x bar or x tilde and set it to 0, then we can define, then this formula, this equation defines all points lying on the plane. And again, from this equation you can see that the scale actually doesn't matter. So if you multiply it by a constant, then we're still getting the same points on the line. Similar as before, we can now normalize this plane equation by saying that the first 3 components, an x, and y, and z, have a length of 1, and then this vector actually corresponds to the normal vector, and if it has length 1, it's a unit normal vector, and then the last coefficient d specifies the distance of the plane from the origin. And then we can also define 3D transformations again. A translation, as before, can be specified by a multiplication of a 4x4 matrix with a vector. For only a translation, you would have the identity in the upper left, and then the 3-dimensional translation vector in the upper right. And then if we replace this identity in the upper left by a rotation matrix, a 3-dimensional rotation matrix, then we obtain an Euclidean transform. Elements of this type are also called to be elements of the special Euclidean group of dimension 3. Just saying that we are dealing here with rotation and translation at the same time. And as before, you can define a scaled rotation where we have an additional scaling factor to grow or shrink objects or trajectories in 3D. You can define an affine transform to stretch to stretch an object, and you can define projective transformations and homographies that are even more general. But for the moment, and mostly for the remainder of this course, we mostly need Euclidean transformations to move around the robot in 3D and to compute motions between poses. So now let's look a little bit more at 3D Euclidean transformations. Obviously the translation, which is a 3-dimensional vector, has 3 degrees of freedom because we can move around the object or the quadrotor along all 3 axes. And similarly also the rotation has 3 degrees of freedom because we can turn the quadrotor around all 3 principal axes. Now, if you look more closer at this rotation matrix, then you see that it actually consists of 9 elements, because it is a 3 by 3 orthogonal matrix. These elements are also, or this group is also called the special orientation group, SO3, because it preserves scale and it preserves the angles. And to read such a rotation matrix, you can look at the column vectors, and then these vectors correspond to the coordinate axis after the transformation. So what do we now typically need to do with rotation matrices? Or what are the operations that we frequently have to apply? Well, of course, one thing, and we've seen that already before, we need to invert them and we need to be able to concatenate them, for example, to integrate the odometry from sensors. And of course, we need to do the inverse. Sometimes we need to estimate a rotation matrix because we want to find out how the robot moved between two time steps. And now the question is, how easy are these operations on matrices? So is a rotation matrix actually the right representation to solve these tasks? And obviously, 3D rotation matrices can very easily be concatenated just by multiplying them, and they can also very easily be inverted. So those of you who have listened carefully will remember that a rotation matrix or an orthogonal matrix can be inverted just by taking the transpose of the matrix, and that's of course a super fast operation. The disadvantage is, and that's especially a disadvantage if you need to find the rotation between 2 points in space, is that it's completely overparametrized. You have 9 coefficients instead of only the 3 real degrees of freedom. So if you use that in an optimization task, then you'll have to make sure that the 9 parameters that you're estimating actually form a valid rotation matrix, and that's usually not very trivial. So the question is, aren't there any other representations that are minimal or that are close to minimal and that simplify, that help us during this optimization problems? And one very common form, and probably also the best known form of such a representation, are the Euler angles. The Euler angles are so the rotation is just a product of 3 consecutive rotations around a predefined order of axes. For example, you would first rotate around the x-axis, then rotate around the y-axis, and then rotate around the z-axis. And especially in aerial navigation, the so-called roll, pitch, yaw convention is very common. And this means that you specify first the roll angle along the main axis of the quadrotor or the plane, then the pitch angle, which specifies the rotation around the wings of the robot, and then the yaw angle that describes the heading of the quadrotor or the plane. So typically you need to convert from Euler angles to rotation matrices and vice versa, and you can do that as follows. So you specify the Euler angles as 3 values: the roll angle, pitch angle, and the yaw angle, and then you use that to compute 3 individual rotation matrices: a rotation around the z-axis, a rotation around the y-axis, and a rotation around the x-axis, and you concatenate all 3 of them. So every individual rotation matrix is very simple because it's just a sine and cosine around to describe the rotation around a certain axis. But if you multiply all of them together, then you get a very ugly expression as shown here at the bottom. And then again, if you want to go back from a rotation matrix to the roll, pitch, yaw angles, then you could use these formulas. There are other formulas as well that bring you there. Because it's overparametrized, it's hard to sometimes to find the best way in the presence of noise for doing that. So the advantage of Euler angles clearly is that it's a minimal representation. You only have 3 parameters, and they have a very easy interpretation, especially when your angles are close to 0, because then you can just imagine in your head how the plane would be rotated or how far it is away from the resting position. The disadvantage is that there are many different Euler representations, and there is typically confusion when somebody sends you Euler angles, because you never know whether he used the XYZ convention or used it the other way around, ZYX, or and so on. So I think there are like 24 different ways of interpreting Euler angles, and that makes it sometimes hard to communicate them in the right way. The other problem is that it's really difficult to concatenate them, because you always have to convert them to a rotation matrix and then do the concatenation there, and then extract again the resulting Euler angles. And the last problem, and that's actually in terms of optimization, the hardest one, is that Euler angles have singularities. They can get locked in a so-called gimbal lock problem, as illustrated here. So it can happen in the Euler angles that 2 axes are being aligned, and then in this situation you're losing 1 degree of freedom. So for example, when these 3 rings here, so each of these rings now describes 1 rotation around, so this is according to the roll pitch yaw formulation. But it can happen that all of these axes then align, and that we're actually only having that we have all of these 3 disks lying in the same plane, and then in this plane you can't rotate anymore around the central axis, around the yaw angle, and this can be very bad, and it can't be solved with Euler angles. An alternative representation, and also quite intuitive one, is to use the so-called axis angle representation. There the idea is that you describe a rotation by a rotation axis, a normal direction vector in 3D, and a rotation angle, theta, that says by how far you rotate around this axis. Well, this representation then has 4 degrees of freedom, because you need 3 degrees of freedom to specify this direction, and a 4th parameter to specify the rotation angle. You can combine both of that together by saying that the length of your axis directly encodes the rotation angle. So a rotation of 0, for example, would just be the 0 vector, and a rotation of 180 degrees would mean that your rotation axis, or that your rotation vector, has a length of pi. And good. So this in this representation, where you just have 3 parameters, is also called the angular velocity representation, or a so-called twist. This is again a minimal representation, but it is not unique. Actually, similarly to the Euler angles, I guess you can imagine why this is the case. So every 2p you repeat the same rotation, because if you rotate more than 360 degrees, then you're again ending up at the same spot. Good. There are again formulas to convert from Euler axis angle to rotation matrices and back. From axis angle to rotation matrices is the conversion formula is called the Rodriguez formula, as given here, and and the inverse is also given here. So for more information, there is lots of more things to be said here, but to keep it simple, and because we don't really need it in the rest of the course, I'd like to refer you to the book of Ma and colleagues, and in particular to chapter 2. And if you Google for this, then you can find an online copy of it. Good. So, as I said, the axis angle representation is also called the twist coordinates. The advantage is it's a minimal representation, and a second advantage is that the derivations are really simple of that. So, especially for optimization problems that we will see later, the axis angle representation is really beneficial. The disadvantage, again, similar to Euler angles, is that it's difficult to concatenate them. You always need to go to a rotation matrix and then multiply them there and then convert them back to axis angle. And the conversion is also fairly slow because you need to compute sine and cosine, which can be, at least on some processes, a costly operation. So a last representation for 3D rotations are the so-called quaternions. A quaternion is a four-dimensional vector representing a rotation. It can be split into a real and a vector part. The real part is just a number, and the vector part is a three-dimensional vector then. And you can normalize them such that the length of the quaternion is exactly 1. And in this case, you can imagine these unit quaternions to be points on a four-dimensional sphere of radius 1. And then there is one ambiguity in quaternions. Opposite sign quaternions actually represent the same rotation. So the unit quaternions actually just live on one half of a sphere, and the other half of the sphere then represents again the same rotations. But otherwise, quaternions are unique. So the really good news on quaternions is that they are easy to multiply, to concatenate, can be easily inverted, and so they are very efficient and very easy to implement. And this is the reason why many onboard or many quadruples that need to do these calculations on board actually use the quaternion representation. For example, to concatenate two quaternions, it's just a small number of multiplications and subtractions and additions that you need to do, so things that you can do fairly easy on an embedded system. Also to compute the inverse is extremely easy. You just flip the sign of either the real or the imaginary part. So two more things that you would like to do with quaternions is to rotate a 3D vector using the rotation represented by the quaternion, and this turns out to be just again a multiplication of the quaternion with the vector and then with the conjugate of the quaternion, which is extremely fast to compute. And if you want to, you can convert, of course, quaternions to the other types. For example, it's closely related to the axis angle representation, but of course you can also transform a quaternion to a rotation matrix and convert a rotation matrix to a quaternion. Good. So to summarize that, there are different representations of 3D orientations or 3D rotations. There is not a single best one. It really depends on your application. If you just need to concatenate things, then rotation matrices and quaternions are very well suited. If you want to optimize a 3D rotation, then the axis angle representation is very well suited. And maybe one thing in general that is good to know, it's even for experts in 3D rotation or 3D geometry, it's really hard to parse or to read a 3D rotation vector, no matter in what representation. So if I see Euler angles, I typically do not know what rotation they correspond with, except for if it's maybe close to the origin. And same holds for a rotation matrix. I guess there are very few people only who can tell you how an object is oriented if they look at a rotation matrix. And it gets even harder for the axis angle and in particular for the quaternion representation. So if you look at something like this, then and you don't know what rotation it is, be assured this is normal and there is no good way of interpreting it manually. But one thing that can help you here, because you need to debug, of course, your programs at some point, is to use good 3D visualization tools. For example, under Linux, when you use ROS, the robot operating system, there is a tool called RVIS. Under C++, there is the libqgl viewer. And of course, for our online exercises, we have this WebGL-based 3D viewer that will help you to determine whether your orientations and rotations are right. Good. Now, the last part in this video is now that we need to be able to do 3D to 2D perspective projections as they happen in 2D or in cameras. So, for example, here we have two objects being located in the world, in the real world, in 3D, and we have a camera actually observing these objects, and then these objects are being projected onto the image plane of the camera, and so we need to find a way to compute from the 3D point in the world the 2D coordinates on the image plane. And the most used model for cameras, that holds for most cameras that have normal lenses, is the so-called pinhole camera model, where you just remove essentially the last component of your homogeneous vector to obtain a two-dimensional homogeneous vector of your point. And then again, x tilde is homogeneous, so we need to divide by the last coordinate to obtain the real coordinates on the image plane. One problem, of course, is so far that if we just down project a 3D point in the world to 2D, the 2D point will still be given in the same units as our 3D point. So, for example, if our 3D points are specified in meters, then also the 2D point will be specified in meters on the image plane. But of course, what we need with digital cameras is the pixel position. So we need to convert this position in meters to a position in pixels. And for that, we need to apply some scaling and some offset. This matrix that does the scaling and offset is usually called the intrinsic matrix. It's sometimes abbreviated with a K, and it consists of 5 parameters, namely the focal length, fx and fy, that specifies, in principle, intuitively speaking, the opening angle of your camera. The larger this focal length is, the smaller the opening angle of your camera is, and vice versa. So a normal camera, for example, like a webcam with, say, 60 degrees of opening angle, has a focal length of around 500 to 1000. Then we also need to specify where the camera center is. This is typically in the middle of the image, but it doesn't necessarily have to be there. It depends on where exactly the lens is mounted and where exactly the sensor is mounted. So during calibration, it makes often sense to calculate these values. And then there can be a skew factor that determines how much, whether or not the pixels on the image array are actually orthogonal or not. But in almost all modern cameras, there is no skew, so this S can be assumed to be 0. And then one last thing, of course, the 3D point coordinates that we've been looking at previously are typically given in world coordinates. So before we can project them onto the image plane, we need to transform them from world coordinates to the local camera system. This transformation is also called the camera extrinsic parameters. So where the camera, and these parameters describe where the camera is located in 3D space. And this is similar to, as we've seen before, the conversion from a global coordinate system to the local coordinate system of the camera. And now we can concatenate all of these transformations. So we have the 3D world PW being transformed into the local coordinate frame of the camera and then being projected to 2D and scaled and offsetted according to the camera intrinsics. And then this homogeneous vector x here gives us the coordinates on the screen or on the image plane. Good. So to summarize the lesson from today or from this video, we've looked at 3D points, lines, and planes. We've also introduced 3D transformations, in particular the Euclidean transformation that we will be using a lot in this course. And then we've looked at different representations for 3D orientations. And as we've summarized earlier, the choice greatly depends on the application that you're looking at. And in the next quiz, we will ask you again to summarize which of these representations you still remember and what the advantages and disadvantages are. And we've also looked at the 3D to 2D perspective projection as it happens in in a normal camera. So these things here that we've looked at today are really important, and you really have to know them by heart. If you had the feeling while watching this video that you didn't fully understand it, then my advice would be to look at the computer vision book of Rick Zeliski, in particular chapter 2. It's fully available online with lots of material, and yeah, then please have a look at that.